This is my Calculus 1 course. Today we're going to continue to learn L'Hopital's rule, and we're also going to learn an alternative definition of the derivative. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So, if you don't have these formulas memorized, go ahead and take a picture of those. And get a picture of the limit laws at the left, and L'Hopital's rule is at the right. If you don't have pictures of those things in your photos file, then you're going to need those right in front of you as we work along in the class today. So we're going to start by doing some review problems on their type of problems we did in the previous class. So we're going to determine if L'Hopital's rule can be used to find each limit, and if so, we're going to use the rule. And if we can't use L'Hopital's rule, then we'll use some other method. So remember, there's a lot of different ways to find the value of a limit. You can use a graph, which is not very practical because you have to draw the graph, and your number that you come up with is not going to be very accurate. And we can also use algebraic manipulation, but in this case we can't really do that. At least it's not obvious how we would do that. And we can also use the limit laws, which in this case are not really going to produce anything. And we can also use limit law number 8, which tells us that if we have a continuous function, we can simply plug in 0 or replace x with 0 and find the limit that way. But if we can't use any of those methods, we can see we don't want to use graphing, we don't want to use algebraic manipulation because we don't know how. When we plug in 0, in this problem we get 0 divided by 0. So in that situation, it's useful to employ L'Hopital's rule. Remember, L'Hopital's rule only works when we get 0 divided by 0, or infinity divided by infinity, or negative infinity divided by infinity, or infinity divided by negative infinity, or negative infinity divided by negative infinity, so on and so forth. So remember, we have to make sure that we have an indeterminate form. 0 divided by 0, infinity divided by infinity, something like that. So we're going to find the limit of the numerator. So we get e to the 0 minus 1, which is 1 minus 1, which is 0. So the limit of the numerator as x approaches 0 is 0. So that checks out. And let's find the limit of the denominator as x approaches 0. So, these are both continuous functions, so we can use limit law number 8. We can just replace x with 0. So again, we get 0. That checks out. So it looks like we can use L'Hopital's rule. Okay, so I'm going to copy that expression up there, and hopefully L'Hopital's rule is going to work for us. Sometimes it works, sometimes it doesn't, but we'll see. You can try it. We know that we can use it because we have 0 divided by 0. If we didn't have 0 divided by 0 or infinity divided by infinity, then we couldn't even use the rule because it only applies when we have indeterminate forms. So L'Hopital's rule says that the limit of that expression is the limit of the derivative of the numerator over the derivative of the denominator as x approaches 0. All right. So we have a function inside another function. So we have to use the chain rule. The derivative of -1, well, that's just 0. But there are 3 steps to the chain rule. We're going to find the derivative of the outside function. The derivative of e to the x is just e to the x. So that's the derivative. That's step number 1, is find the derivative of the outside function. Step number 2 is to keep the inside function. We don't do anything with it, it just stays there. And the third step is to multiply by the derivative of the inside function. The derivative of 5x is 5. So we end up with that. And we do the same thing with the denominator. So at this point we could actually just plug in 0 or replace x with 0. But I'm going to do one more step here. We can actually use exponent rule number 2 if you remember the numbers of the exponent rules. So exponent rule number 2, I forget if we use Roman numerals or numbers. I think we used Roman numerals in my intermediate algebra course. And we can subtract the exponents. Because the bases are the same, they're both e, we can subtract the exponents. 5x minus 2x is 3x. So that's not a trick, it's just a basic math principle. So now we can use exponent or limit law number 8 and just plug in 0. And 3 times 0 is 0, e to the 0 power is 1, and we have 5 halves. We had to kind of rush forward there because we're out of room. So we used L'Hopital's rule successfully on that problem. Again, we're just doing some review. And this problem was a little bit different because we had to use exponent rule number 2. We didn't have any problems in the previous class. I don't think that where we had to do that. We didn't have to do it, but it just made the expression simpler. Okay, so we first need to confirm, if we're going to use L'Hopital's rule, we need to confirm that we get an indeterminate form. So let's find the limit of the numerator as x approaches infinity. Now, as x gets bigger and bigger and bigger, this fraction is going to get closer and closer to 0. The yellow expression is going to get closer and closer to 0. And so the answer is just going to be 10 to the 0 power, which is 1. So it's pretty obvious that that's what's going to happen, but if you want to, you can use limit law number 7. So limit law number 7 says that if you have a composite function, which is this yellow expression here, and you're finding the limit of that expression, then you can just put the limit inside the or next to the inner function. That's what that means. So we can use limit law number 7 if we want to, if it makes you feel more confident with that. And then we have 10 to the limit of 15 over x as x approaches infinity. So this limit, again, is just 0. So we have 10 to the 0 power, which is equal to 1. So what does that mean? Well, it means we can't use L'Hopital's rule because 1 is not 0 and it's not infinity. And just for good measure, let's figure out what happens to the denominator. We don't really have to well, we're going to use the information eventually anyway, so I guess we need to find what the limit would be anyway. So we can do the same thing. We can use limit law number 7 and put this limit actually inside here. But again, we don't really need to do that. We know that as x gets bigger and bigger, this fraction is going to approach 0. And so if you're trying to find the limit, by all intents and purposes, we can just let it be 0, and we have cosine pi over 3 minus 0, which is equal to cosine pi over 3, and that's equal to 1/2. So again, that tells us that we can't use L'Hopital's rule. So we have to use some other method, And the method that we're going to use is the limit laws. So let me copy this. So the limit laws tell us that the limit of that expression is the limit of the numerator over the limit of the denominator as x approaches infinity. So we know what these limits are. I mean, we already found them. So the top limit is going to be 1 and the bottom limit is going to be 1/2. So all that became 1, all this became 1/2, and simplify, and we get 2. Okay, so we did not use L'Hopital's rule on that problem. And we can cross out L'Hopital's rule because we're not using it. All right, so let's try one more of these problems before you try one on your own. So let's find the limit of the numerator and see what happens. And if x is a really big number and you raise it to the second power, then you just get a bigger number. And e to some really, really big number is just a really, really big number. So the limit is infinity. And we don't have to rectangle these answers. The limit of the denominator as x approaches infinity is going to be infinity. Now, how do we know that? If you graph the natural log function, you can see that this graph is just going to keep going up and up and up. It's never going to stop. So it looks like we can use L'Hopital's rule. So L'Hopital's rule tells us that the limit of that expression as x approaches infinity is equal to the limit of the derivative of the numerator over the derivative of the denominator as x approaches infinity. So we have to use the chain rule here because we have a function inside another function. So when we use the chain rule, we find the derivative of the outside function, which is just e. Remember, the derivative of e to the x is just e to the x. And so that's the first step. The second step is we keep the inside function. And the third step is we multiply by the derivative of the inside function. So the derivative of x squared is 2x. And the derivative of natural log x is 1 over x. Okay, so now we need to simplify the complex fraction, and you should know how to do that by now. So you're a calculus student, and calculus students should know how to simplify a complex fraction. If you don't know how to do it, then figure it out quickly, because we learned how to do that back in beginning algebra. A lot of calculus students don't know how to deal with this, but if you're coming from my curriculum, then you know what to do. Remember, we have e to the x squared times 2x, and then divided by 1 over x. This fraction symbol can be thought of as a division operation. Again, so many calculus students don't know things like that, and if you don't know that, then that's a sign of a problem with your previous instruction. And I forgot my limit notation here. So what is the limit of this expression? as x approaches infinity. Well, if you take a big number, raise it to the second power, you just get a bigger number. And if you raise e to that power, you just get a bigger number. And if you multiply that by x squared, you just get a bigger number. So it just gets bigger and bigger and bigger, and our answer should be positive infinity. Or we can say the limit does not exist, because a limit has to be a finite number, or else it doesn't really make sense to say that the limit exists. So now it's time for you to try. So again, I'm going to give you one more chance to take a picture of the differentiation formulas and the limit laws at the left and L'Hopital's rule at the right, and get a picture of these two problems that we did. And go ahead and try number 4. You can use number 3 to help you. And when you come back, we'll do it together. Okay, we're back. Okay, if you got that right, excellent. So get a picture of these two problems, and I want you to try number 5. Now for number 5, we're not going to be able to use L'Hopital's rule, so I want you to explain to me, as we did in this problem over at the left, why we're not able to use L'Hopital's rule, and then find some other way to find the limit. You could use the limit laws, limit law number 8. You're not going to be able to use algebraic manipulation for any of these problems, but try number 5, and when you come back, we'll do it together. Okay, we're back, so our limit is going to be 1. So if you got that right, excellent. Okay, I want you to try one more of these types of problems. In this problem, you're going to need the chain rule when you find the derivative of tangent x squared, because we have a function inside another function. So we have to use the chain rule. Now if you forgot the derivative of the tangent x function, again, you can look at your differentiation formulas. So down here, you see that? So take a picture of those formulas. You see that we need those formulas from time to time, and you have to have them. So try number 6, and when you come back, we'll do it together. Okay, we're back. Okay, if you got that right, excellent. So the limit was 0. Okay, so now we're going to go on to one-sided limits. So as I mentioned, L'Hopital's rule works for one-sided limits also. You can see down here, L'Hopital's rule can be applied to one-side limits also. So we have a one-sided limit. Why? Because we have that plus sign. That means x is approaching 4 from the right. But there's a big question that students will have, and that is why? Why do we need a one-sided limit? Why do we need a one-sided limit? I mean, what's the point? Well, the reason we need a one-sided limit on this particular expression is because x can approach 4 from the right, but it can't approach from the left. There's no such thing as approaching from the left. And the reason for that is, if you look in the denominator, let's plug in a number like 3, which is approaching 4 from the left. then we get square root 9 minus 16, which is square root negative 7. That's an imaginary number. You can't have a negative in a root. So if you were to graph this function, the graph doesn't even exist to the left of 4, so you can't approach 4 from the left. There's no such thing as approaching 4 from the left. So that's why you need a right-sided limit on this particular problem. But let's see if we can use L'Hopital's rule. So let's figure out what the numerator approaches as x approaches 4 from the right. And this is a continuous function, so we can just plug in 4, and we get 0. So far it seems that we can use L'Hopital's rule. Let's find the limit of the denominator as x approaches 4 from the right. And again, we have a continuous function. Continuous at least when x is 4 or greater than 4. So we have root 16 minus 16, which is root 0, which is 0. And we don't have to show all that because we don't really have the room anyway. So the numerator approaches 0 as x approaches 4 from the right, and the denominator also approaches 0. So we can use L'Hopital's rule. Okay, so I'm going to copy this expression. And bring it down. And L'Hopital's rule tells us that the limit of the expression as x approaches 4 from the right is equal to the limit of the derivative of the numerator divided by the derivative of the denominator as x approaches 4 from the right. So the derivative of natural log 4 is just 0 because that's just a constant. The derivative of natural log x is 1 over x. And here, if we change that to a 1/2 power, I'm not going to do that because you should know how to do that by now, really. And I don't know if we have the space for that. But if you do all that, you're going to end up with 1/2 times x squared minus 16 to the negative 1/2 power. And you have to use the chain rule because we have a function inside another function. So we have to multiply by the derivative of x squared minus 16. Which is 2x. So we have 3 steps for the chain rule. We find the derivative of the outside function. That's step number 1. Step number 2, we keep the inside function. And step number 3, we multiply by the derivative of the blue expression, the inside expression. And that's the limit as x approaches 4 from the right. Okay, so if we simplify, we have in the denominator x over the square root of x squared minus 16. That's a complex fraction. So if we simplify, we get the square root of x squared minus 16 over x squared. And we can use limit law number 8 and just plug in 4. And let me find some more room here. And we end up with 0. Sorry, we're kind of scrunched in there. So again, that needed to be a one-sided limit because we can't approach x equals 4 from the left. We have to approach from the right. Now in this problem we have the opposite situation. We can approach 1 from the left, but we can't approach from the right. So this negative symbol here means we're approaching from the left. So x equals 1 is here, and we're approaching on the number line. We're approaching from the left. It's not really a dot that's approaching, but you get the point. But the question is why? Why can't we approach from the right? Well, if you choose a number that's bigger than 1, say you choose 2. So we're approaching from the right, so let's say we plug in 2 for x. Then we get root negative 16 plus 1, and then we get root negative 15. That's an imaginary number, so the expression doesn't exist when you plug in numbers that are bigger than 1. So you can't say that x is approaching 1 from the right because the expression is not even defined when x is bigger than 1. So you have to approach from the left. So go ahead and try number 8, and when you come back we'll do it together. Okay, we're back. So we get 0. 1 to the 4th power is 1, negative 1 plus 1 is 0, and 1 to the 3rd power is 1 times negative 2 is negative 2. So we have 0 over negative 2 is 0. So if you got that right, excellent. Okay, so we had one-sided limits, and the reason they were one-sided is because the expression was not even defined when x was bigger, or in some cases smaller than the value in question. So here we have a left limit, and here we're dealing with situations when x approaches a vertical asymptote. So you have some graph, and maybe the graph does something like this. So that's a vertical asymptote when the graph approaches some vertical line, some vertical dotted line, and in this case we're approaching 0, so maybe we should move this over. So we're approaching 0 from the left. So in this case the answer would be positive infinity. The limit would not exist. But if you're approaching from the right, the limit in this case is negative infinity. So it turns out that there's no two-sided limit for this problem. The two-sided limit does not exist, and that's because the left limit, approaching 0 from the left, is going to give us a different result than approaching 0 from the right. And so you can't just write 0 without a negative symbol on it, because that would mean that there's a two-sided, that the two-sided limit exists. It doesn't exist because the left limit and the right limit are different. So that's why we have to use a one-sided limit in this case. Because again, if you look at the graph, one part of the graph might be going up or it might be going down, but the other part of the graph, as x approaches 0, is going down the other way. So that's the situation we have here. Now, if you had a situation where coming from the left and the right, we were going up, then the two-sided limit, you could say it's infinity. Or if we were going down from both left and right, you could say that the two-sided limit is negative infinity. But in this situation, we don't have that, so that's why we need a one-sided limit. So we have a continuous function here. So we can just plug in 0 for x. And so far it seems that we can use L'Hopital's rule. So let's determine what's happening to the denominator as x approaches 0 from the left. So again, we have a continuous function, so we're just going to plug in 0, and we get 0. So it seems that we can use L'Hopital's rule. So I'm going to copy this expression, and we'll try to use L'Hopital's rule. Okay, so L'Hopital's rule tells us that the limit of that expression is equal to the limit of the derivative of the numerator, and we can write it as x to the 2/3 power over the derivative of the denominator as x approaches 0 from the left. So we have 2/3 x to the negative 1/3 over e to the x, and let's change the form of this so we can understand what's going on. So we're going to have 2 over 3 times the cube root of x times e to the x. So if we let x approach 0, this expression is just going to approach 1 because e to the 0 power is 1. So x is going to get closer and closer to 0, which means this expression is going to get closer and closer to 1. This expression, however, is going to get closer and closer to 0. So what you'll have is 2 over 3 times an expression that's getting closer and closer to 0 times an expression that's getting closer and closer to 1. So you have 2 over 0, but that is undefined. Now, if we approach from the right, we're going to get positive infinity. So what happens if we approach from the left? Well, again, because x is approaching 0, this expression is going to approach 1, because when x eventually equals 0, the green expression will just be 1. But the cube root of a negative number is a negative number. For example, the cube root of negative 27 is negative 3. So you're going to be producing a negative number as you approach 0 from the left. So what that means is that when you approach from the left, the expression is actually going to approach negative infinity. So if you were to graph this, you would probably have something that looks like this. So from the right, you approach positive infinity. From the left, you approach negative infinity. Something like that. So that's why we have to choose. Are we approaching from the left or are we approaching from the right? In this case, we're approaching from the left, but again, we get different answers depending on where we're coming from. So our answer is negative infinity, or we can say the limit does not exist. Okay, because we're over here. Alright, so I want you to try a problem like that. For number 10, we have a similar situation where the right limit might be positive or negative infinity, but the left limit is going to be a different sign. So see if you can figure out why. Try number 10, and when you come back, we'll do it together. Okay, we're back. So in this case, our answer is going to be positive infinity. So why is that? Well, if x approaches 1 from the left, say you plug in 1/2, well, you get a negative number in here. The fifth root of a negative number is a negative, and so this expression would just be getting smaller and smaller in the negative direction, or I should say bigger and bigger in the negative direction. But since we're approaching from the right, we're going to have positive numbers here as this expression explodes. The denominator is going to get closer and closer to 0, which means that the expression is going to become very, very big. But is it going to be big in the positive direction or the negative direction? That's the question. So if you got that one right, excellent. Okay, so now we're going to briefly talk about the rare cases, the rare scenarios where we use L'Hopital's rule. So if we look at L'Hopital's rule, we see that we have these 4 scenarios. We have this scenario here, this one, and this one. But in all the problems that we've done so far, we've only dealt with this scenario and this scenario. So we're going to look at those over here. So this scenario up here is when x is approaching some finite number, in this case a, and f of x is approaching 0, which is also a finite number. So you have x approaching a finite number, and you have f of x approaching a finite number. The other situation is when x approached infinity or negative infinity, and f of x also approached infinity or negative infinity. So if one is a finite number, the other is a finite number. If one is an infinite number, the other is an infinite number. Those are the 2 scenarios that we've dealt with. We haven't dealt with these scenarios, and I just want you to be aware that these scenarios do exist. However, you don't really see them very often for multiple reasons. So let's deal with the first situation. We're just going to do one problem to show you what these look like. So x is going to approach a finite number, but the expression is going to approach positive or negative infinity. So we'll analyze that situation, and then we'll deal with the other situation in the next problem. So I just want you to see what this looks like. So here, let's find the limit of the numerator as x approaches 0 from the right. And notice that we have a one-sided limit again. So this is another example of a one-sided limit. But why? Why does x have to approach 0 from the right? Why can't it approach from the left and the right? Well, that's because if you graph your natural log function, you see that the function doesn't exist over here. There is no graph. That you can't have 0 or negative numbers in a log function. It doesn't make any sense to say that x can approach 0 from the left, because there is nothing in terms of the expression over here at the left. So what happens, we can see with the graph what happens. I guess I should have kept that graph. But as x approaches 0 from the right, what happens to the expression? Well, it goes to negative infinity. So that would actually be negative infinity. I guess we can just keep that graph. And what happens to the denominator as x approaches 0 from the right. Well, that's just going to be positive infinity. But how do we know that? It's easiest to see if we graph the function. So I guess we can graph y equals 1 over x. And from the right, the graph approaches positive infinity. From the left, it approaches negative infinity as we approach 0. So that's why we get positive infinity. And here we get negative infinity. But we still have negative infinity over infinity, so we can use L'Hopital's rule. So again, we have a finite number. Look at this, these purple numbers, finite. They're 0, right? So that's a finite number, but our expressions are approaching infinity. So that's that rare situation. And, you know, one of the reasons that this is a rare situation is because this is a complex fraction. If you simplify it, you get one of those indeterminate forms that I was telling you about. In this case, we get 0 times, well, first of all, if you simplify the complex fraction, you get x times natural log x. So as x approaches 0 from the right, x obviously approaches 0, and natural log x approaches negative infinity. So you have a product of 0 and infinity. That's one of those indeterminate forms that I told you we're not going to study. If you write it in this form, then you have that weird situation where x is approaching a finite number and we have negative infinity over infinity. So let's use L'Hopital's rule and see what happens. So we want the limit of the expression as x approaches 0 from the right. And L'Hopital's rule tells us that we can find the derivative of the numerator and the derivative of the denominator, like so. And so we have 1 over x over negative 1 over x squared. And we can simplify that expression so we get negative x. And now it's really easy to find the limit. We can just plug in 0 because that's a continuous function. So we plug in 0 and we see that the limit is 0. So there you go. Okay, so again, that's a rare situation. You're not going to see those very often because we don't really write expressions where a complex fraction has not been simplified. And we'll do this one together. I'm not going to make you do either of these on your own, although you could try if you want. You're perfectly capable of doing it, but you're just not going to see these, so I don't really need you to do these on your own. But we're now going to do the situation where x is approaching infinity, but our limit is actually a finite number, 0. So this is another case where if we simplify the complex fraction, we would get this, and that's actually really easy to deal with. But if we have this situation, it's actually going to make it harder, but I'm just going to show you what happens when we have this complex fraction here. Again, I just want you to see what this looks like. So we get 0 for the numerator, and x is approaching a really big positive number. So if you have a really big positive number that you're plugging in, well, obviously it becomes negative with a negative in front of it. So you have e to the really big negative number. But remember, if you have a negative number in the exponent, then it goes down and you have e to the really big positive number, but this is going to be a very big number, which means that the entire fraction is going to approach 0. So kind of complicated. A lot of complications going on there. And that's why students typically feel that this is a challenging part of the calculus course. But we can use L'Hopital's rule. So I'm going to copy that information and bring it down. And we'll see what we can do. So again, we're going to use L'Hopital's rule. So we get -1 over x squared and e to the, or negative e to the negative x. And this is a complex fraction. So when we simplify, first of all, the negatives are going to cancel out. If we change this to a positive exponent, then we end up with e to the x over x squared. But this expression is even more complicated than if we just simplified the complex fraction in the first place. So that's why you don't really see these types of problems, or you don't see these types of scenarios, because it's easier to deal with the problem rather than going directly to L'Hopital's rule. But we're going to have to use L'Hopital's rule again. Because we have infinity over infinity again. So I'm not going to show all the work because that would take forever, but so derivative of e to the x is e to the x, derivative of x squared is 2x. Then we're going to use L'Hopital's rule again. And find the derivative. Again, we have infinity over infinity. So then we get the limit of e to the x over 2 as x approaches infinity. And you can see that the numerator is just going to get bigger and bigger and bigger, and the denominator is not going to change at all. So we have positive infinity. Or we can say the limit does not exist. Okay, so again, you may wonder, why are we going over this if you're not going to be tested on that stuff? Well, I just don't want you to be left wondering about those other situations. They're kind of a curiosity, but they do occur from time to time. You'll see problems presented. It's mostly just to help learn L'Hopital's rule, not to really solve problems that you're going to see. Okay, so now we're going to learn an alternative definition of the derivative. This relates to limits, so it's a good time to cover this. This is really mostly for the advanced placement test. Any calculus course could cover this, so it's probably a good idea to go over it. But this is really mainly just to prepare you for the advanced placement test. Now let's do some review. This is the definition of the derivative. It's the foundation of the calculus curriculum. We learned this in a previous class towards the beginning of the course. And let's explain where this formula comes from. This is the instantaneous rate of change of a function at some x value. And let's see where we came up with that. So we have the graph of a function f of x in red, and we have 2 points on the graph, and this line through those 2 points is called the secant line, and the slope of that secant line is defined to be the average rate of change of the function between these 2 points. Now, this point we're going to call x comma f of x. Now remember, f of x is just the y values of the graph. And because our x value is x at this point, our y value is going to be f of x. Now, as we mentioned towards the beginning of the course, function notation is really confusing for students who are taking their first calculus course. But this is just the notation that is used, so we have to get used to it. Now, this x value is the distance that you see here. This distance here. And if we add h to that x value, then that gives us this x value, x plus h. And if we have x plus h as our x value and this point up here, then f of x plus h is our y value. So these are the coordinates of this point here if we add some h value to our original x value and get x plus h for our x value. Now what we're going to do is we're going to take this point and we're going to move it down the graph so that it gets closer and closer to this point here. And in order to do that, we're going to make h smaller. You see, h is smaller over here. It's getting smaller and smaller. And these 2 points are closer together. But then we're going to make h even smaller. Look down here, h is even smaller now. And you can see that these 2 points are getting even closer together. And when h equals 0, these secant lines are then going to become the tangent line, the line that is tangent to the graph at this point here. Now, the slope of these secant lines, like I said, is the average rate of change of the function between those 2 points. But the slope of the tangent line is defined to be the instantaneous rate of change. It's not defined that way. It actually is the instantaneous rate of change of the function at the point of tangency, which is this point here. And again, this is when h is equal to 0. So the slope of the tangent line is the derivative of the function at the point of tangency. And when we try to find that slope using our typical formula up here that we learned in my beginning algebra course, we get 0 divided by 0. And so we have to find the limit as h approaches 0. And we have methods to do that, but that's where we come up with this formula here. So how do we come up with that formula? Well, we're going to find the slope of these secant lines using our slope formula that we learned in my beginning algebra course. If you have a line, you find 2 points on the line, x1, y1, and x2, y2 that you see here, and plug those coordinates into this formula and you get the slope, the rate of change of the function as x changes. Well, now instead of x1, y1, and x2, y2, we're going to use these points. We've specially tailored those points and their coordinates. So now we're going to plug in the coordinates of these 2 points here. So we're using the same formula that we used. We're just replacing the yellow y2 with the yellow f of x plus h, and replacing the blue y1 with f of x, and so on and so forth, using these points. You can use any of these points here. And when we do that, you see that the x's in the denominators cancel out, and we're left with this expression, Again, it's the slope of the secant line, the average rate of change of the function between those 2 points. But we want h to approach 0, and we want to figure out what happens to this expression as h approaches 0. So that's the limit of the expression as h approaches 0. That's the slope of the tangent line. So again, this is all review. We learned this in earlier parts of the course. Now we're going to change this notation to f prime of x, because that's the derivative. So there we have the derivative of the function at some x value. So that's our definition of the derivative. Now it turns out that we can make another formula if we want to find the value of the derivative at a specific x value. This expression here, or this formula, gives you an expression for the derivative of the function at any x value, assuming that the derivative exists, or the function is differentiable at that x value. So this gives you an expression. For example, if you have f of x, this expression or this formula will give you, let's say you have x squared, this formula will give you 2x. So it's an expression in terms of x. But this formula down here uses a specific x value, a. We're calling it a now. So this expression down here will not give you or this formula will not give you an expression in terms of x. It will give you an actual number. For example, if a is equal to 5, then the expression should give you 10. So this will give you an actual number. But why do we care about that? I mean, who cares? This formula is nothing new. It looks exactly the same. We just replaced x with a, right? Well, you're right. It's not exactly necessary to write a new formula for finding the derivative of a function at a specific x value. But it turns out that we can come up with a different form of the definition of the derivative if we're trying to find the derivative of a function at a specific x value. We have this form here, which we're going to see, and we're going to use, but we can come up with a different form that you're going to see also. So let's figure out where that form comes from. So we have the same situation as we did before, same graph, same points, but we're going to rename these points. In the previous problem, this point was x comma f of x, but now we're switching. We're making this point x comma f of x. And this point is going to be a comma f of a, and what that means is we know the coordinates of this point. A is a letter that represents a constant. X is a variable. We can change x, but a is constant. We can't change it. We're assuming that that's a constant. So we know the coordinates of this point, and we're trying to find the derivative of the function at that point, the instantaneous rate of change. So we're just setting things up differently. So we don't have an h value. We're not allowing h to approach 0. In this case, we're going to let x, this length here, we're going to let x approach a. So we're going to bring this point in just like we did before. We're going to bring it closer and closer to the other point. But to do that, we're going to let x approach a. So you see x is getting smaller and smaller to the point where it's approaching a. It's getting smaller and smaller, and then when x is actually equal to a, then this secant line becomes the tangent line. So you can look over that if you want, but in the same way that we found the slope of the secant line to start out with, we're going to find the slope of these secant lines using our formula for the slope of a line given 2 points. But now, instead of using x plus h comma f of x plus h, and x comma f of x, we're going to use a comma f of a and x comma f of x. And we come up with this expression here. Again, you can just look at these 2 points. That's where we're coming up with that. This is the exact same thing we did before. It's just using a different type of notation. Now, again, I don't really want to complicate things by showing you this, but the College Board, they love to show you these types of things on the advanced placement test, so unfortunately we have to look at this. And you may see this outside of the College Board world, the advanced placement test, so, it is something that it's good to know. But it does kind of complicate things a little bit. So now we have this expression which represents the slope of the secant line. But if we find the limit of that expression as x approaches a, as you can imagine, that's going to give us the slope of the tangent line, which is the instantaneous rate of change of the function when x is equal to a at that particular point. And we can change this notation to f prime of a, just like we did in the previous example. So we have this expression, which is the alternative form of the definition of the derivative. And we can summarize this. So we learned this formula in the earlier parts of the course. So if you have f of x, for example, is equal to x squared, f prime is equal to 2x. So we know that based on this formula, this formula takes us to that point. Now we have shortcuts. Obviously, we learned the power rule. But if you wanted to prove that that's true, you would use this formula. This formula gives us an expression for the derivative of the function at some x value. But these expressions, this one is based on this. We're just replacing x with a. And we also have this other expression. These expressions, they give you an actual constant. So for example, if you wanted to find f prime of 3, given that f of x is x squared, f prime of 3 should be 2 times 3, which is 6, right? F prime of 3 should be 6. So these two expressions here, they give you actual numbers, not an expression, but an actual number. So let's demonstrate how these expressions work. So I rewrote the expressions up here, and we're going to show that they both give you the same thing. Again, we can only come up with this new alternative version of the definition of the derivative if we're finding the derivative at a particular x value. It only works if you're finding a derivative at a particular x value. Same with this expression here, given that we have a plugged in. It's designed to find the derivative at a particular x value. But this one, again, is based off this formula, whereas this one is completely new. So let's demonstrate. So it says here, if f of x is x squared, use the formulas below to find f prime of 3. So we're going to use our new formula first, because that's actually an easier formula to use when you're doing this type of problem. So we've never done anything like this. These formulas are very familiar, but we've never actually tried to find f prime with these formulas directly. What we did is we found the derivative using our differentiation formulas. We used the power rule in this particular example, and then we just plugged in 3, and we got our answer. That's the fastest way to do it. But in these problems, we're actually going to find the derivative the long way using these formulas for finding the instantaneous rate of change of a function at a specific x value, x being 3. So we're going to let a equal 3. So we're just replacing a with 3. Okay, and now we can replace f of x with what f of x actually is. It's x squared. So that's easy. We're just replacing it with x squared. Now what is f of 3? Well, f of 3 is the value of this expression when x is equal to 3. So it's just 3 squared. Okay, so we have the limit of x squared minus 9 over x minus 3 as x approaches 3. Now we can find the value of this limit using L'Hopital's rule. So why don't we just do that? Why don't we use L'Hopital's rule, where I don't want to use any tricks right now to find the derivative. I just want to show you that these formulas work the way that we use them at the beginning of the course. So we're just going to use algebraic manipulation. So using algebraic manipulation, we can factor in this particular example. Now again, there's a lot of different types of algebraic manipulation, so it depends on the function that you're trying to find the derivative of. It just so happens that this expression is going to be a factoring problem. Okay, so we have the difference of two squares we're factoring, and you can see that these expressions, they cancel out, or these factors cancel out. So we're left with the limit of x plus 3 as x approaches 3. And that's really easy to find. You just plug in 3, and we have 6. Okay, so that's what we expected to find. Remember, the derivative when x is 3 should be 6, because the derivative of x squared is 2x. So we found that this green formula works. It's just another form of the definition of the derivative. But again, it only works when x is a specific value. So now let's use the other formula. That's the formula that's based on the expression that we learned, but we're just replacing x with a. So let's see if we get the same exact number. We should get 6 in our final answer. So a is 3. So I just replaced a with 3. And now this is where students tend to have some problems. F of 3 plus h, that's the same thing as f of x. F of x is x squared, but f of 3 plus h is 3 plus h squared. That's where students really have some problems. But again, this is review. We've done this before in this course. So f of 3, that's just the same thing that we found over here. That's just 3 squared. You plug in 3 into the function. And so f of 3, that became that. So now we just have to find the limit. And again, we'll use algebraic manipulation. We could use L'Hopital's rule. So in this example, we're going to expand, or with this formula, we're going to expand. In the other with the other formula we just had to factor, but with this formula we have to expand. So it's a different way of finding the derivative. Okay. So I expanded, and the 9s are going to cancel out. And we have a polynomial divided by a monomial, and we could factor out the GCF and then cancel out the h's, but when you have a polynomial divided by a monomial, you can just divide each term. It's not really necessary to factor it out. That takes longer. So we have 6 plus h. 6h divided by h is 6, and h squared divided by h is h. So now we can just plug in 0. So we get 6 plus 0, which is 6. So that's what we expected. That's the same thing we got over here. So you can see that those two formulas, they do the same thing. They're just different ways of finding the same value. Okay, so let's do some practice problems. It says here, interpret each of the following expressions. You may use math notation. So I've rewritten the formulas up there, the new formulas. And so what this is asking us to do is asking us to figure out what this expression represents. And you can see it looks an awful lot like this green expression here. So what it represents is the derivative of the function when x is equal to 95. That's it. It's that simple. That's all I want you to write. Now here we're using this orange expression. That expression is the derivative of the function when x is equal to pi. Alright? That's all that is. Now here we're going back to the green expression. This is the derivative of the function when x is equal to 2. And here we're going back to the orange expression. That expression is the derivative of the function when x is equal to negative 10. So we're just getting used to these formula. So now we have the derivative of a function g. We're using a different letter. Sometimes that's done. And again, we're using the green formula. We're finding the derivative of the function g when x is equal to negative 2/3. Now, why does it say x plus 2/3? It should say x minus 2/3, right? Well, that's because we have a double negative. We have x minus negative 2/3, which is x plus 2/3, so you have to be careful about that. That can be confusing. Okay, now we have an expression where we're using the orange formula, but instead of f, it's p. So this is the derivative of the function p when x is 1/2. P is often used for position. We're going to use that, possibly we'll use that later on in the course when we do applications of some more applications of differentiation. Okay, and now we're going to use the green formula again, but our function is now a. So this is the derivative of a when x is equal to e squared. And then we're going to use the orange formula again. That expression is the derivative of m when x is equal to root 10. Alright, so I want you to try some of those problems. As you can see, they're not really difficult. It's just you're getting used to these formulas. That's the whole point of this, is to get used to these formulas. So try number 21. 21 is going to use the green formula there. Or you're going to need the green formula to figure that out. So try 21. When you come back, we'll do it together. Okay, we're back. So that expression represents the derivative of the function when x is equal to 17. So if you got that right, excellent. So this expression over here is going to use the, it's based on the orange formula. So try number 22. When you come back, we'll do it together. Okay, we're back. So that expression represents the derivative of the function when x is equal to 6. So if you got that right, excellent. Go ahead and try number 23. So for number 23, it's kind of tricky because there's nothing being subtracted here, right? Well, that's because our x value is 0. So we're subtracting 0, but the 0 just disappears. So that's kind of a tricky one, so be aware of that. So try number 23. When you come back, we'll do it together. All right, we're back. So that expression represents the derivative of the function when x is equal to 0. If you got that right, excellent. Try number 24. And when you come back, we'll do it together. Okay, we're back. So this expression represents the derivative of the function when x is equal to -2. So for number 25, again, it's kind of confusing because we have x plus 12. That's because it's a negative number, so x minus -12 is x plus 12, so just be aware of that. Try number 25. When you come back, we'll do it together. All right, we're back. So this expression represents the derivative of the function when x is equal to -112. If you got that right, good. Try number 26. And when you come back, we'll do it together. All right, we're back. So this expression represents the derivative of the function when x is equal to 2e. So if you got that right, excellent. Try number 27. When you come back, we'll do it together. Okay, we're back. This expression represents the derivative of the function when x is equal to 7 pi over 4. So if you got that right, excellent. Try number 28. And when you come back, we'll do it together. All right, we're back. So this expression represents the derivative of the function when x is equal to -2.3. So if you got that right, excellent. Okay. Let's do some more problems. I've got the formulas up there. If each limit produces the value of the derivative of f at x equals some x value a, identify f of x and a. So we have a limit here, and it represents the derivative of some function f of x. What is the function? Well, we can see what it is. This is employing the green formula. We can see it's natural log x. That's the function. So immediately we can see, as long as we can identify what formula we're using, we know the function, it's natural log x. And we're also supposed to figure out what a is. Where are we finding the derivative? If we find this limit, it's the derivative of the function at what x value? Well, obviously, we just look for a. It's in 3 different places, so we're finding the derivative of the function natural log x when x is equal to 9. Okay. So again, these are problems that are just designed to get you familiar with the formulas. So we used the green formula in that example. Now we have an expression that looks more like our orange formula. So what is the function? Well, we have 7 plus h cubed. That's going to tell us something about f. we'd like to look at this expression here, but that's just a number. That doesn't really do much for us. So what this tells us is that the function is x cubed, because we're cubing. And this number here is 7 to the third power. You can verify that. So we're finding the derivative when x is equal to 7. We can see this number here is 7, so that's the giveaway. So again, the whole purpose of this is to get you familiar with these formulas. Okay, so now we're using the green formula. So what is f of x? F of x is 1 over x. And we're trying to find the derivative when x is equal to, we just look at this number here, when x is equal to 4. Of course, we can also look at these numbers. Okay, now we're using the orange formula, because I see the h's, and I see h's approaching 0. So what is the function? Well, it looks like we have 5 to the x. Again, it's hard to see. It's harder to see with the orange formula, but it looks like it's going to be 5 to the x, and we're finding the derivative when x is equal to -3. We can see the -3 there. And then down here, it looks like our function, we're using the green formula so we can see what the function is. It's just e to the x. It's a lot easier to see using the green formula. That's one of the benefits of that formula. And we're finding the derivative when x is equal to -11. Now you see it says x plus 11 because we're subtracting a double negative. So now we're going to refer to this orange formula. F of x is going to be determined by this expression here. That's cotangent x. And we're finding the derivative at pi over 6. So there you go. All right. So now we're going to use the green formula again. So what is the function that we're finding the derivative of? It's root x. And we're finding the derivative when x is equal to 8. Okay, let's do one more of these. Now we have h's, and h is approaching 0, so it's probably going to be the orange formula. And it's harder to see what f of x is, but we can see the natural log. So it's a good bet that this is going to be the natural log function. And we're finding the derivative when x is equal to 6, because we have the 6 there. So, time for you to try some problems like that. The first problem here is going to, you're going to need to refer to the orange or the green formula and see what you can do. Identify the function you're finding the derivative of and the x value where you're finding the derivative. When you come back, we'll do it together. Okay, we're back. That tells us what the function is. So go ahead and try number 38. You're going to need to refer to the orange formula for that one because we have h's. So try 38. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 39. We're going to need to refer to the green formula for that one. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. So now we're going to need to refer to the orange formula for number 40. Try number 40. When you come back, we'll do it together. This is a little harder, I guess, but we'll see. Try 40. When you come back, we'll do it together. Okay, we're back. So you can see this -3 here. That's A. Okay. Now don't be confused by number 41. It says x plus 5 rather than x minus 5. Why is that? Well, because we have a negative x value that we're approaching. So this is going to be x minus -5, which makes it x plus 5. So try number 41, and when you come back, we'll do it together. Alright, we're back. So if you got that right, excellent. So now we're going to refer to the orange formula because we have h's. So try number 42, and when you come back, we'll do it together. Alright, we're back. If you got that right, excellent. Alright, I want you to try number 43. We're going to be using the green formula, so try 43. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Try number 44. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay. So now we're going to proceed with this. It says find the following limits with L'Hopital's rule, the differentiation formulas, and algebraic manipulation. So we're going to find the value of this limit using 3 different methods. And you can see that there's more than one way to do this. So you're going to see something like this on the advanced placement test if you take the advanced placement test. And a lot of students are not going to realize that there's more than one way to do this. The fastest ways are L'Hopital's rule, or to simply recognize this as the derivative of the function root 7x when x is equal to 2. So we're looking for x prime of 2. That's the fastest way to do it, but a lot of students may not recognize it as the derivative of the function root 7x when x is equal to 2. So they'll be left to use L'Hopital's rule. And if students don't know L'Hopital's rule, or if they don't remember to use L'Hopital's rule, or that if they don't recognize it as the derivative of the function root 7x when x is equal to 2, then they're going to have to use the long way, algebraic manipulation. And realistically, you don't have time to use that method on the multiple choice part of the exam. And you're not allowed a calculator. You can't graph this expression on this portion of the exam when you see these types of problems. So you're going to need to know which method to use. We're going to demonstrate all 3 of them just so you can see that there's more than one way to do it, but you want to choose the fastest method, obviously. So let's first use L'Hopital's rule. But I don't want you to get in the habit of using L'Hopital's rule without confirming that we get an indeterminate form. You cannot use this rule without confirming that we have an indeterminate form. Turns out we have 0 divided by 0 here, but we need to confirm that. So the limit of root 7x minus root 14 as x approaches 2 is 0. I'm not going to do all the math because you can see just by looking at it that it's going to be 0. We don't have enough room on the page to do the math anyway. So the limit of the numerator as x approaches 2 is 0, but the limit of the denominator as x approaches 2 is also 0, and again, we don't need to do all the math because you can see that. So we confirmed and we confirmed. So we get 0 divided by 0. So we can use L'Hopital's rule. So remember, L'Hopital's rule tells us to find the derivative of the numerator and the derivative of the denominator. So I'm going to rewrite the limit. And I'm going to rewrite this expression as 7x to the 1/2, because it's easier to find the derivative when we have powers, right? So I rewrote that. And now we'll use L'Hopital's rule, finding the derivative of the numerator and we had to use the chain rule because we have a function 7x inside another function, the root function. So the first step is find the derivative of the outside function. Second step, keep the inside function. And third step, multiply by the derivative of the inside function. A lot of students think that they can escape from the chain rule. You can't escape. Derivative of root 14, well, that's just 0 because that's just a constant. Derivative of x minus 2 is just 1. Well, now, if we simplify, we end up with 7 over 2 times the square root of 7x. So that's just basic math. The negative power comes down and turns into a root. That's all stuff that you should know. Well, now we just plug in 2. And our final answer, when we reduce and everything, we get root 14 over 4. So there you go. When we rationalize the denominator, you should get root 14 over 4. So that is L'Hopital's rule. That's probably not the best way to do it, but that is one of the faster ways to do it. So now let's use differentiation formulas. This is actually the fastest way to do it. So we need to recognize this as the derivative of the function root 7x. And of course, as we just explained, that's the same thing as 7x to the 1/2 power. Let's find the derivative. We already did that, so we know what it's going to be using the chain rule. And then we get 7 over 2 times the square root of 7x. So we have the derivative. And now we just want to find the value of the derivative when x is equal to 2, so we just plug in. So this is very similar to what we just did, really. And long story short, we don't have to show all the steps on that, but we end up with root 14 over 4. We got the same exact thing. But we can also use algebraic manipulation. That's the long way. So there's all kinds of ways to do this. I just want you to see that, you know, you have to choose wisely and understand the methods that you've learned, because you don't want to use the long method on the advanced placement test. These are the short methods over here, but the long method is what we learned at the beginning of the course. Algebraic manipulation. So this is the method where we use a lot of different things, but in this example we're going to have to multiply both sides of the expression by square root 7x plus square root 14. And you have to be really careful when you do this. You have to use parentheses. Okay, and so now we're going to use FOIL. We're going to multiply these two, and we get root 7x squared, and then we're going to multiply these two. And so we get root 7x times root 14, and we'll multiply these two. We get negative root 7x times root 14, and we'll multiply these two, and we'll get negative root 14 squared. And we can just keep the denominator in the factored form. So you can see this method is really not desirable. That's why we use all the differentiation formulas. So when you square a square root, it just gets rid of the square root. It's just 7x. These terms cancel out, and when you square a square root, again, you just get rid of the square root. Okay, so now in order to see what to do here, we have to factor a 7 in the numerator, and you can see what's going to happen. So these x minus 2's are going to cancel out, and we're left with 7 over the square root of 7x plus the square root of 14. So now we can let x equal 2. We can go off to the right here. As soon as x equals 2, we get rid of the limit notation, and at that point we have 7 over 2 root 14, and when you simplify you get root 14 over 4, which is exactly what we got in the previous problems. So when you see this problem on the advanced placement exam, there's all kinds of ways to solve it. But obviously you want to recognize it, recognize the function, or use L'Hopital's rule. They're probably counting on you using L'Hopital's rule. That's how these problems are really designed. Okay, now let's try another one. So in this problem we recognize this because it looked like the green formula, right? In fact, we'll bring that down and write that next to that problem. So that was that type of problem. We had to refer to that new definition. But in this problem, we're actually using something that looks more like the old definition of the derivative. We're just plugging in a constant value for x. So let's first use L'Hopital's rule. We need to confirm that we have an indeterminate form, and I'm not going to do that, but you can plug in 0 for h and confirm that. We also need to figure out if the limit of the denominator equals 0, and that's obviously 0, so it checks out on both of those. So now we can use L'Hopital's rule. So I'm going to copy this. So because we have the indeterminate form, we can find the derivative of the numerator, and we'll have to use the chain rule. So we'll find the derivative of the outside function, keep the inside function, and then multiply by the derivative of the inside function, but the derivative is just 1. And the derivative of that is just 0, so that just goes away. Derivative of h is 1. So now we can simplify, and we get 2 times -1 plus h, and that's it. And you can use brackets if you want to. So now we can actually get rid of the limit and just plug in 0 for h. So we have 2 times -1 plus 0, which is -2. Alright, so that's using L'Hopital's rule. That's probably the way that the College Board wants you to do that. But there's actually a faster way to do it. Using the differentiation formulas. If I recognize this as the derivative of the x squared function with -1 plugged in, because I think about this formula here, that's going to be faster. So if f of x is equal to x squared, then f prime of x is equal to 2x, and we have this -1 here. That's a, so we're trying to find the derivative when x is equal to -1. Plug it in, and I've got my answer. So you can see that that was a lot easier, a lot faster than even the L'Hopital's rule. Now algebraic manipulation, again, it's going to be a lot more involved. So why can't we just use the fastest method? Why do we have to do all this stuff? Well, it's because the College Board wants you to get used to these problems. We're not going to do every single type of problem that you'll see on the advanced placement test, because that would be a whole different course, but we are going to do a few of these. So in this example, we're going to expand, so we end up with the following expression. So we expanded all that to that, and so this is not going to be quite as involved as the algebraic manipulation on the previous problem. All of these problems can go a lot faster. You don't have to take this much time. I'm taking a lot of time because I'm showing you how to do the problem, and we have to write it out, but you don't have to write every step necessarily. So we can plug in 0 for h, and then we get -2. So you can see we got the same answers. But which one do you want to use? Well, obviously the fastest method is the differentiation formulas. Alright? So I want you to get a picture of this problem here, and get a picture of this problem here. For the next problem, you're going to use the green formula as a reference, so I'm going to paste that. And you can use that here. Now, when you use algebraic manipulation, you're going to have to deal with this expression. It's the difference of two cubes. You can factor using this formula. We don't usually use that formula. It's not very common, but technically you're expected to know it, even though no student really remembers that. We went over that earlier in this course. So you can factor the difference of two cubes, or you can divide this expression by this expression using long division. And it may have been a while since you saw long division. So if you don't remember how to do it, then obviously use factoring. You can also use synthetic division, which is a faster version of long division. So try number 47. Obviously, if you don't remember synthetic division, then you're not going to be able to use that method, but see what you can do. When you come back, we'll do it together. Okay, we're back. Okay, if you got that right, excellent. You didn't have to do all three of these methods. I just showed those in case you want to see them. So try number 48. When you use the method of algebraic manipulation, you're going to have to simplify this complex fraction, and you may come across some roadblocks, some problems there, but see what you can do. When you use L'Hopital's rule and you find the derivative of this, it may be best for you to change that expression to 5 plus h to the negative 1 power, or you can use the quotient rule. So try this problem, and when you come back, we'll do it together. Okay, we're back. Okay, if you got that answer, good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And number 2. And number 3. And number 4. And number 5. And number 6. And number 7. And number 8. And number 9. And number 10. And number 11. And number 12. And number 13. And number 14. Number 15. Number 16. And number 17. But don't go before you get your homework. Remember, if you don't do the homework, it's 100% guarantee that you'll learn absolutely nothing in the entire course. So get a screenshot of this here. That's screenshot number 1. And screenshot number 2 of the homework. And screenshot number 3 of the homework. And screenshot number 4 of the homework. And number 5. And number 6. But don't go before you get the answers. Remember, your homework must be done correctly. If you do the homework incorrectly, that means you didn't do the homework. So you must check your answers. Here's the answers. And we have one more page. So those are all the answers to the homework. Again, get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.